You know, whenever you're developing a new product, there's always this classic debate, right? On one side, you've got the push for just simple, brute force power, and on the other, you have the argument for a more elegant, more intelligent design. Today, we're going to dive right into that very conflict, and we're going to center it on a surprisingly brilliant engineer, the common cockroach.
All right, so to really unpack this, we're going to tell the story through two different voices. First, we have a skeptical, very pragmatic product manager, a PM, who basically lives by the quote you see on the screen. And battling it out with them is a passionate systems engineer, someone who truly believes that nature has already solved some of our most difficult problems.
So, our story kicks off with the engineer going to the PM with this totally new, kind of radical idea for an airflow system. The engineer says, instead of just running a fan, what if we made the entire system breathe? And you can just imagine the PM's reaction. Breathe? What does that even mean? We're building a machine, not a lung. In this slide, this just perfectly captures their two different worlds. The PM is all about the path of least resistance. More power, bigger fan, simple mechanics. It's proven and we get to market faster. But the engineer sees that as a huge missed opportunity. They're thinking, no, that's just the brute force way. A smarter design could give us way better performance with less power and, believe it or not, even less complexity.
Well, the PM is totally unconvinced and pushes back. Okay, smarter flow sounds nice, but what are we actually talking about here? Where is this brilliant idea even coming from? To which the engineer replies, it comes from the American cockroach. And you can just feel the pause in the room. You cannot be serious.
Oh, but the engineer was dead serious. I mean, look at this. The cockroach's respiratory system is an absolute marvel of efficiency. It doesn't breathe continuously. Instead, it uses these tiny little valves called spiracles to open for just a short burst and then close for a much longer time. This duty-cycled breathing, as they call it, means it uses 40% less oxygen and it naturally keeps dust out. It's a system that's been perfected over millions of years.
And the results of this are just staggering. In that short little window when it's open, the cockroach pulls in 91% of the oxygen available. I mean, that is the kind of ruthless efficiency that engineers dream about. The goal isn't just to move air, it's to get the absolute most out of every single breath.
So how do you actually make a fan breathe like a cockroach? Well, you don't need to build tiny mechanical valves. That would be a complete nightmare. Instead, the engineer explained, you just translate that biological idea into software. Using a pretty common technique called pulse width modulation, or PWM, you can control the fan's power by sending it these really fast electrical pulses. By just changing how long the on pulse is, you can make the fan speed up, slow down, or turn on and off in a really precise rhythm, basically mimicking the cockroach's breathing with nothing but code. And after a whole lot of testing, this is the exact logic they landed on. It's so simple. You run the fan at a really low 20% power for 10 seconds, and then you just turn it completely off 4 or 5 seconds. You just repeat that over and over. This simple on-off cycle is the engineering version of that cockroach's hyper-efficient breathing. But of course, this is exactly where the product manager raises the first, most obvious objection. I mean, the core belief in hardware has always been that more is more. So the PM says, I don't get it. You're deliberately turning the fan off. Why wouldn't we just use a more powerful fan, run it all the time, and just get this done faster? This feels like a huge step backward. And the engineer's response is just perfect. Because more isn't always better. When you just blast air at something, you create turbulence, all these chaotic swirling pockets of air that actually stop particles from being captured. It's like trying to catch a feather in a hurricane.
And the engineer came prepared with data. These computer simulations really show the power of this cockroach method. Okay, so pulsing the flow cuts turbulence by 44%. But here's the kicker, the real magic number. Look at particle residence time. That off phase lets the air totally calm down, giving particles over 200% more time right near the capture surface. It's not about moving air faster. It's about giving the particles time to actually get captured. So that's the whole point, right? The goal isn't just to move air past a filter, it's to give the filter time to work. By pulsing the air, you create this calmer, much more deliberate flow that is just dramatically more effective. It's not about moving less air, it's about making the air you do move really, really count. Okay, so the PM is starting to buy into the logic, but then they raise another really valid concern. They're basically trading one kind of complexity for another.
The PM says, look, I get the fluid dynamics argument, but now you've added a layer of software and firmware that we have to develop, test, and maintain. A simple on-off fan is just simple. Is this new system really less complex?
And the engineer's response? Let's look at the lab results. On the left, a traditional fan just running continuously. On the right, our cockroach-inspired pulsing fan. Power consumption just plummets from over 3 watts to just about 1 watt. And check out the motor temperature. It's running more than twice as cool. That means less stress, less wear, and a longer product life. So from the hardware's point of view, this is way simpler. And this is where it all comes together for the person actually using the device. The pulse system isn't just more efficient, it's also quieter. A 3 decibel drop is actually very noticeable to the human ear. And on top of all that, it actually captures more particles. It is just better in every single way that a user would care about. And the engineer drives the point home. So it's not more complex, it's more intelligent. By adding a few lines of code, we got rid of the need for a more powerful motor, for better heat sinks, for more sound dampening. The system works less, but it achieves more. That is the very definition of elegant design.
Lab data is one thing, but the ultimate test is always the real world. So the engineer presented the final piece of evidence. The results from a 50-unit pilot program they ran in apartments in East Delhi. First off, the system didn't just meet its efficiency goals, it absolutely shattered them. In the real world, it used 62% less power than even the most optimistic design target. That is a massive real-world saving.
Second, this directly addresses the PM's concern about practicality. Because the system was so effective and ran so gently, it took way longer for things to clog up. They projected users would need to do cleanings every 45 days. The reality? The average was 78 days. That is a huge win for user convenience.
And finally, the ultimate verdict on the user experience. 91% of the people in the pilot program reported that the device was barely noticeable, especially at night. It just did its job silently and effectively, which, for this kind of product, is the holy grail.
So, faced with just this overwhelming pile of data, from simulations, from the lab, and from the real world, the product manager finally conceded. They just said, "Okay, you have my attention. The data speaks for itself. Let's build it."
This story is just such a powerful reminder that sometimes the best engineering solutions aren't found by adding more power, but by looking for more intelligence. And it leaves us with a really fascinating question. In a world that is obsessed with more, bigger, and faster, what other complex problems could we solve if we just learned how to breathe a little smarter?